So let's talk about the near boiler piping now. And this is critical because back in the day when they made steam boilers, they made them specifically for steam systems, not for hot water systems. And the difference was the steam boiler had a very large outlet to allow the steam to leave the boiler at speeds no greater than 15 feet per second. That was the standard back then. And the goal is if you're under 15 feet per second, the water is not going to leave with the steam. It's not going to get sucked out of the boiler by the high velocity steam. A steam boiler also had a big steam disengaging space, what we call a steam chest, where the steam could rise off the surface of the water and have this kind of a cavern to play around with before it left through that really big hole. And the steam boiler also had very wide sections internally so that the steam bubbles that were formed down where the fire is could rise up through the section without creating a lot of turmoil on the surface. So after the OPEC oil embargo in the 1970s, we began to see hot water boilers being used on steam systems with just the changing of the trim. So now suddenly we had boilers that sure operated at higher efficiency because they contained less metal and less water, but they were also subject to higher velocity steam because the exit holes were smaller, the steam chest was diminished, and the sections were much more narrow internally. So we started to see a lot more surging and priming of water, which is water getting sucked out of the boiler. So the boiler manufacturers, since they couldn't do it in their manufacturing facility because they had to meet the government standards for efficiency, they began to tell the installers that you now have to follow proper near boiler piping techniques to remove the water from the boiler, from the steam before it gets out into the building. So the water is definitely going to get sucked out of the boiler by the steam, but we've got to catch it in the near boiler piping and put it back into the boiler before it gets out. So let's look at a practically perfect drawing. This is from the New York City Housing Authority, which is loaded with steam heating systems. And I've been looking at this drawing probably for 30 years, and it's practically perfect. And what I like about it is we can go step by step and show all the elements of good near boiler piping. First, notice that we're taking two risers to the header. Now the header is this pipe that's horizontal, that's going to carry all the steam, and note that it's offset through two screwed elbows. The reason why we use screwed black iron pipe here is because that header is going to expand at a different rate than that boiler. And unless we've got something to play with where these elbows can turn a little bit, that header will put incredible force down on these pipes and which will act like a crowbar to actually rip the boiler sections apart, and the boiler will begin to leak. So we offset here, and this is why I hate to see copper fittings being used on near boiler piping, because the soldered fitting definitely will loosen up as time goes by and come apart. I've seen too many of them. Now this is the takeoff that goes off to the system, and notice it's made between the last riser coming up off the boiler and this pipe, which we call a header drip, and an equalizer, which is going to take any carryover water and put it back into the boiler. We never take any connection to the steam system between the risers that go off to the header because we want everything going in the same direction. Steam and any carryover water comes out of here, goes that way, goes that way. If we were to have this connected here, the steam would be going this way with the carryover water, this one would be going that way with the carryover water, and we'd wind up with a big glob of water here that would get thrown out into the system. The boiler would then go off on low water, we'd have water hammer out in the building, and lots of problems. So, one of the rules I like to follow is that you should always have a minimum of 2 feet of space, vertical space, between the top of the boiler and the bottom of the header. Now, some manufacturers say 2 feet of space between the water line and the bottom, but I don't think that's enough, and I'm going to prove it to you in a minute. So 2 feet of space there. Now over here, we've got the piping that's going to take the steam up into the building. It's good to have a full-size T here because if you reduce the pipe right at that T, Bernoulli's law is going to kick in. The same thing that made those ejectors work on those steam engines that we talked about earlier. So if you've got a sudden reduction in pipe size, the velocity of steam will pick up and you'll suck water out into the building with the steam. So we want to reduce it a point above that. Carryover water gets thrown back into the boiler, into this pipe, which is called an equalizer. Now, this is an equalizer because you've got steam pressure inside the boiler that's pushing down on the steam water line, the boiler water line, trying to shove the water out of the boiler. Now, the equalizer's job is to put a force back here to shove that water that's trying to escape back in. So it's kind of like having a scale with the same amount of weight on both sides of the scale. This is also why it's good to keep the amount of fittings in the equalizer to a minimum so you don't have excessive pressure drop through there, and never to put valves or anything like that in here. So just a turn and a drop down, keep it big so that there's less pressure drop through there, and that's why we've got this equalizer there. Back in the day, they would put a check valve here in the return to stop the water from backing out of the boiler, but they found that the check valve would often fill up with goop, and the goop would cause the check valve to stay open and the boiler would lose its water. And during the time of coal-fired boilers, we have no low water cutoffs yet, so that's a dangerous thing. So that's where the equalizer came to be. On the return piping, over here, you see it comes up into the equalizer, several inches below the boiler water line. This position is set by the boiler manufacturer to get it above the crown sheet, which is where the fire is, and in a safe position. And this came to be known as the Hartford Loop, because the Hartford Steam Boiler Insurance and Inspection Company, which is one of the few companies in the world that would actually insure steam boilers at a time when they were blowing up every day and a half, they began to mandate this at the beginning of the 20th century, because they, before that, the return water came back into the bottom of the boiler, and if a return line should break, all the water would leave the boiler, and suddenly you had the potential for a boiler explosion. So they said, let's bring it back into here, very close to the boiler water line, so should a return line break, the water can only drain to this point. It's kind of like siphoning the water out of a swimming pool. If this were your siphon hose, when you got to that point with your water line, it would stop draining the pool. So it brought them the advantage of having time to notice that there was something wrong. So that's called the Underwriter's Loop or the Hartford Loop in this day, and it's still being used today, and it's still a great idea, because even though we have a low water cutoff, there's a chance that this might fail or get plugged. So the Hartford Loop can save lives, and it did over the years. At the top and at the bottom, we've got two valves, and I think these are essential to any steam boiler. This is a return valve, and this is called a king valve, like it's wearing a crown. And it's not anything special. It could be a gate valve or not a glow valve, but a gate valve or a butterfly valve. That's called a king valve because it's the main valve for the whole system. And what that allows us to do is once a year to close these two valves and to be able to blow all the mud out of the boiler. And for that we use ideally a full-size valve here, a ball valve, which you take the handle off of it once you install it so that nobody bumps into it by accident, because the steam system is open to the atmosphere, and the steam is constantly causing the iron and the steel to corrode, and all that corrosion washes down by gravity and winds up in the bottom of the boiler in what's called appropriately the mud leg of the boiler. So this is mud that's made of metal, and it's very, very thick, and it will not just drain out by gravity. So if you tried to just open the mud leg valve without having any steam pressure in the boiler, the weight of this water, which is not much, because a column of water 28 inches high only exerts 1 pound of pressure. So from here to the mud leg, maybe you've got 2 pounds of water weight. So 2 pounds of water weight is not going to move this mud out of the boiler. And that drastically cuts down on the life of the boiler, because the mud prevents the water from circulating properly, and you wind up with sections that get too hot and they begin to break. So by using a king valve and a return valve, once a year we can go back, close these two valves, isolating the boiler from the system, build up about 10 pounds of pressure in the boiler, and then open the mud valve. And when you do that, all that crap's going to get blown right out of the boiler. So if you're selling boilers to customers, it pays to talk about these valves, because it adds a little bit of price to the installation. Actually disappears in the price of the installation, but it's going to dramatically increase the life of the boiler by having them there. So in your customer self-interest, definitely talk about that. And while you're at it, talk about this additional valve down here, because we could work with the return valve and this drain valve over here to waste the condensate, because when we put in a new steam boiler, it begins to act like a scouring pad on the old system, and all that crap that's up in the system is going to work its way back. And why put all that crap back into the boiler when we can catch it with the return valve and drain it out of here for a few days? So these valves here really make a big difference on a replacement steam boiler. Over here we have, because this is an apartment building, we have to use two pressuretrols. One is the operating pressuretrol. Now the steam system typically operates, say, between 1/2 psi, that's the cut-in setting, and 2 psi on the high side. And this is wired in series with the thermostat. So whatever controls the, let's get some heat signal to the building, whether it's a heat timing device or whether it's a thermostat in a room, that sends a signal which starts the burner off. The burner is going to fire until we reach whatever pressure we set the pressure control to. And as I said, the Empire State Building only needs 2 pounds. So your building, if it's smaller than the Empire State Building, probably needs a lot less than 2 pounds of pressure. So we set that at the minimum, and on the standard pressure control, that minimum would be, say, a 1 pound differential. So if we're cutting in at a ½ pound, which is the lowest setting it can have, the boiler will cycle between 1/2 pound and 1.5 psi. So as long as the thermostat's calling, the boiler will cycle between those 2 points. It's called the cut-in setting, which is typically a ½ pound, and the cut-out setting, which would be a 1.5 pounds. Now, when the thermostat gets satisfied, the burner just shuts off, and everything just cycles back down to 0. So that's the way the pressure control works. Now, the reason why we've got a backup pressure control here is this one would be set to, say, 10 psi, and it's only set to cut off the burner, and it has a manual reset button on it. Now, the purpose of that is because it's an apartment building, and people who live in apartment buildings are more valuable than people who live in single-family homes, because the code requires that we have 2 pressure controls watching out for them. In case one of the pressure controls fails, we need the backup pressure control to shut off the burner if we ever get to 10 psi. Because if we get to 15 psi, that relief valve is going to pop. And a relief valve on a steam boiler is not like a relief valve on a hot water boiler. Hot water boiler relief valve is kind of friendly. You know, it sputters, it spits a little bit and then stops. A steam relief valve is jack in the box. And it's a scary, evil jack in the box, because when that opens, it is sized and designed to dump that entire boiler load instantaneously into that boiler room. Now, I say that to you because if you work on these steam boilers, one thing I want you to always do is keep the boiler room door open. Because if you're in a boiler room with the closed door, when that relief valve pops, the temperature in that room is going to go from whatever it was to 250 degrees instantaneously, and all the air in that room is going to be displaced by that high pressure steam coming out at 15 psi. And that will kill you instantly. So don't be in that room if that relief valve pops with the doors closed. So one complaint here is, you notice on the bottom here, they've got what's called a pigtail, and we're looking at it from the side, so you really can't see it. But a pigtail would be looked down in the front like a pig's tail. It's curved like that. And its purpose is to fill up with water and keep the latent heat of the steam from reaching through to the control. So it extends the life of the control dramatically over the years. The reason why you see it positioned this way with the donut hole on the side is because back in the day when we used mercury type switches in these, if we had the hole looking at us like we were looking at the donut right now, when the pipe heated and expanded, this control would actually tip left and right, which would mess up the mercury and screw up the settings. So they moved it this way so that when the control goes, it moves toward you and back away from you, front to back, rather than side to side, which doesn't affect the mercury switches. But notice that this pigtail probably will clog up, because they almost always do. And when it does, it's going to take offline both the operating pressure control and its backup. So this is not a good place to save money on pigtails. If you've got 2 pressure controls and a gauge, they should be on 3 separate pigtails. Down here we've got clearly this is a McDonnell Miller automatic water feeder and low water cutoff, and its job is to maintain a minimum water line. So it's set up on these quick hookup fittings off the gauge glass to feed at a minimum amount of water level, and that's to replace water that gets lost by minor leaks and evaporation, because steam systems are open to the atmosphere, so there's always going to be evaporation. So that's not designed to maintain the center of the gauge glass or 2/3 of the gauge glass. When we start out on a steam boiler, we begin at a level that's about 2/3 full, because think about it, the water that's between the 2/3 and the 1/3 is out in the building as steam, heating the radiators. When it comes back, we want it to have a place to go inside the boiler. So if a feeder were to feed at the 2/3 point, when the water came back from the system as condensate, it would flood the boiler. So the automatic feeder is set at a minimum level, not at the operating level. And this, according to the manufacturer, needs to be blown down every single week, because it will fill up with mud. And if it's not blown down every single week, it's going to cause the feeder to fail, and it's going to cause the low water cutoff to fail, and that's going to create a problem, and that could burn down the whole building. Now, this is an insurance picture that was sent to me by the people at McDonald and Miller. This is the float that's supposed to operate the automatic water feeder and the electrical cutoff to the burner. This is what screws into the bottom here. So this was what was never blown down. You could see that the blow-off valve was never open because this is the mud, and this is the consistency of this stuff, and this is sitting under the float, so the float just sits in it like it's sitting on the ground. So the water level went down, the burner kept firing because there was nothing to shut it off. The boiler began to glow cherry red. It heated the pipes. The pipes got hotter and hotter. They came in contact with wood, and they set the building on fire. The insurance company came. People said, we've got insurance on the boiler. Insurance inspector opened the low water cutoff and told them that their policy was canceled because clearly they never blew down this boiler. So be careful. This is near boiler piping done really, really well. And I'm going to show you a series of photographs that were posted by people that put them on the wall at heatinghelp.com on our bulletin board. And these jobs are just done really well. Now this piping arrangement that you see here is called a drop header. And the drop header is taking the two risers that go up to the header and turning them to make the header lower. And this gives you more rise out of the boiler, which is going to give you drier steam. And it also, even though it involves a few more fittings, makes it easier to make all your connections because you got more wiggle room here to put things together, and it gives you a better approach piping to the steam mains. So this continues along here. This is the part of the header, and there is the header drip and the equalizer that goes down into the Hartford Loop, which you see down here in the corner. So that's a really well done job. It's photographed before it was insulated, just to give you a sense of what's going on here. Here's another drop header. Notice that we're trying to get this pipe to go up as high as possible before it turns to go into the two takeoffs to the system. So we've got two mains, and we go off with two pipes off the header. One goes left, one goes right. We don't go off with one and make a turn through a bullheaded T left and right up above. And again, nothing gets connected to the system between this pipe, these two pipes. Here's an even nicer one. Look at this tremendous rise up here to dry out the steam, and then an oversized header to really dry out the steam, to slow the velocity, put the water back in the boiler, and the two takeoffs out to the system. You see the pride taken in this job. Just they paint the pipes before they insulate them. Who's going to see that except the guy that installed it? Knowing that, there's also this, and I hope you don't recognize any of your own work here as I show you these next couple of slides. But this was put in. This boiler failed because it was the sections were separated, and that was because there's no on the header here. There's no offset, so we've got the takeoff coming out of the boiler over here, another one going over here. There's no offset, so this pipe expanded, and this acted like a crowbar to separate the boiler sections. Notice too that they're doing their takeoffs to the system between the risers, such as they are going up. So if steam's coming out of the boiler at say 60 miles an hour, bringing water with it, notice how the steam knows to go left as the water goes to go right, because I guess they're going to install arrows on the inside of the pipe to direct the steam this way and the water that way. I don't know how that's possible, but this guy got paid, so there. So did this guy. This guy posted this, and he's complaining about the manufacturer, Peerless, that they don't make good boilers. But look at the way he piped it. Peerless makes great boilers. But look at this. Where's the 24 inches from the top of the boiler, or even from the gauge glass? Where's my offset? You're piping in copper. All this stuff's going to come apart. How do you make water go that way if steam's going this way up into the building? So this is just nuts. But this is what people do. They don't read the instructions. Here, look here. How about this? Huh? Homemade. Look at that. Look at that. Notice how water's going to flow uphill here. I mean, this is just crazy, but this is what you see out in the field. And here, look, this is magnificent, right? Where's the header? Is that the header there? This is crazy. This is put in by a good hot water guy who never did a steam boiler in his life, but he gets to work. This one was done with no equalizer, no Hartford Loop, DWV, drainage copper, drainage fittings. And the whole thing falls apart, but the guy got paid. I mean, I once saw a steam boiler get installed with PVC plastic. Gave the woman a good price. It lasted one cycle, and then it looked like a bowl of linguine, the PVC piping. But don't, this is America. We don't have a heating policeman running around looking at this stuff. You've got a plumbing inspector, electrical inspector. Nobody's looking at these steam boilers and how they get installed. You want to be good, all you got to do is follow the directions. And to show you how critical this is, I want to bring in our friends from Weill McLean, who have the good grace to bring around to the trade shows, mostly in the Northeast where there's a lot of steam, this glass pipe steam boiler. And this was done by them in Pyrex piping. They spent a lot of money on this to show you what goes on in a perfectly piped, very clean, brand new boiler. This is reality. So this is the stuff you can't see when you're not looking through glass, but this is what happens. There's your offsets, and no drop header here, but there's the steam header. This is going back into a boiler feed pump that's on their trailer. We don't have a building, so we're going to send the steam off into the parking lot. And as soon as the system starts up, notice how the water begins to come out of the boiler. And this is within a moment of the boiler starting up because of the velocity in a modern boiler. This can't be avoided. A few seconds later, the water line is up to here. A few seconds after that, it's up to there. A few seconds after that, these pipes are completely filled with water. This is normal. And it's spilling over into the header. You see the water up over here. And now we're running, and this pipe is filled with water right up to the elbows. Can you imagine if you didn't go for this 24 inches off the top of the boiler? Can you imagine if you put your header down here? You wouldn't have a steam boiler. You'd have a hot water boiler. There'd be no steam going out to the building. And it's going over here, and this is the way a normal steam boiler operates. So that's the takeoff going out into the building, or in this case, into the parking lot. And you can see this tremendous amount of water being carried over and spilled back into the boiler, or into the boiler feed pump in this case. Now up here, this is what dry steam looks like. So when you're looking at a gauge glass on a boiler, it should look that dry. Dry steam is a technical term. It means that there's no more than 2% liquid water in that steam. Now, since the 80s, boiler manufacturers have not been able to produce boilers that produce that level of dry steam, which is why they encourage you or mandate you or beg you to do this near boiler piping to make sure that you're getting rid of the water before it hits the building. So that's what it should look like in the gauge glass. You shouldn't see any water spewing over the top. You shouldn't see anything floating above the water line in the gauge glass above the top. It should look dry like that, like you're looking at air. So my buddy Mike over here, he's going to do an experiment. He's going to close that valve, and he's going to build up about 5 pounds of pressure inside the boiler just to show you what happens when an automatic valve suddenly on a steam system decides to open. I'm not a big fan of motorized valves in steam heating systems. And the reason is watch what happens when he opens that valve. And this happens faster than you can snap your finger. He opens that valve, and all the water in that boiler winds up in the parking lot. This goes faster than you can blink, faster than you can clap your hands. All of that water explodes out of there, and it goes out into the parking lot. And the cars are getting washed, and everything is... It was very dramatic. I mean, the crowds love this. And notice this fella over here coming in on his phone. He got a lesson in situational awareness when he walked right into this. So imagine this going up into a building. What the problems you'd have uneven heating, you'd have water hammer, you'd have high fuel bills, and all because somebody didn't follow the instructions on the near boiler piping. It's so easy to be successful with this stuff. All you got to do is read the directions and do what they say. And here, they're running 2 pounds of pressure, and you can see the gauge glass is barely moving, and they cut a porthole in this, which is kind of neat because you can see what's going on inside the boiler. There's fury in there. It's like the end of the world going on in there. So just follow the instructions and you're going to be okay. And even on a small boiler, this was at another show, again, Weill McLean. This is a boiler like somebody would have in their little house, and the water's just filling right up to the top and blasting out into the parking lot. All you got to do is do what they say.